Hello everyone. So, why do we do this? So why are we doing this in doing proofs about type theory and type theory? So the first question is, who checks the checkers? Who ensures the safety of our proof assistants, like Agda or Koch? And that brings us the idea of kind of bootstrapping, similar to how compiler actually have bootstrapping for compiling them, a program, the compiler in itself. However, there is a problem with this, and it's the incompleteness theorem from Gödel, and it says that we need a meta theory, that is the theory we do the proof in, to be stronger than the object theory, which is the theory we prove about. But disregarding this, how can we achieve this bootstrapping? How can we find this difference, or how can we see this, minimize this difference between the object and meta theory? So the second part of our title is the decidability part, the decidability of conversion. And conversion is the classical relation for equivalence between expressions. This is an important property for type checkers, to be able to ensure, to check the actual equivalence of types. And this is fairly straightforward for non-dependent functional programming languages. However, for dependent type languages, there's a bit of a problem. For instance, types can depend on terms, which means that we might need to evaluate the terms to be able to get a type. And there's also no unique type for a term. So for instance, these two types are convertible, and they are both convertible for 0, or they're both the type for 0. So what we have done in this paper is that we have proven decidability of conversion. And we have done this by proving an equivalence between an algorithm for a conversion checker and its algorithm, and the formulation of it as a relation with a inductively defined conversion relation. We have done this in the proof assistant Agda. We have done this using a Kripke-style local relation. Okay, so how does these two languages we are working differentiate? So we are doing a proof, our proof about type theory lambda pi un, and it's a type theory which consists of the pi types, the dependent function types, and the natural numbers, and a single universe. And how these differentiate from Agda is that Agda consists of also of sigma type, which lambda pi n doesn't, as well as inductive types and identity types. Something also Agda consists of is induction-recursion, which is a key component for accomplishing our proof. So looking closer at the lambda pi n language, we have the pi type with the classical lambda and applications. We have the U, which is our universe or types of types, and it consists of our type of a system. We also have the natural numbers with 0 and successor of 0, or successor of a natural number. With also the natural recursion. We all had this convenient sugar for it. So we are going to have a little bit of an example here using it. So let's define T to be this natural recursion over N, such that its type is of U, the universe. And for the 0 case, we have a type A. And for the successor case, we have a nut arrow B, and B is the recursive case for this recursion. So this would effectively fold to be, for any number n, be the number of n's, a chain of n's, or nuts, with a at the end. And what we would like to accomplish with this is that we would like to be able to achieve conversions, proof conversion for 0 applied to t to be convertible with a, and successor of n of t to be convertible to n not arrow t of n. Okay, so let's look into our what system defined. And we have the classical judgment of a system, and these are defined inductively as rules. So we refer to these as well-formedness, as well as conversion are part of these judgments. And our conversion consists of equivalence rules, congruence rules for the constructs, as well as beta reduction, eta equality, and net-ret recursion. We also have weak-head reduction, which corresponds to the computational part of our type theory. And these reduce expressions to a weak-head normal form. And a weak-head normal form is that we only reduce to a weak head, so some constructor, but we don't reduce further. So we don't, for the successor of t, we don't reduce t any further. And we also use type reduction in our system. And this effectively lets us prove that the reductions are subsumed by conversion. We also define a relation which corresponds to our algorithm. So our algorithm is a conversion checker, and basically how it works is that it reduces the expressions to a weak-head normal form, and then it compares them syntactically. And our relation consists of any transitivity rule, because that wouldn't really correspond to our algorithm. So what we want to prove now is that we want to prove that this algorithmic equality is indeed an algorithm by proving decidability for it. And we would also like to prove that this indeed corresponds to conversion by proving equivalence with it. However, there's a bit of a snag at this point, and it's that we require two properties. We require normalization, and we also require pi activity. Normalization being the property that we can compute some u for any t, and u is in weak-head normal form, so that t reduces to u. And pi activity is the property such that if we have two convertible pi types, we have the components of the pi types convertible as well. So to get these properties, we introduce what we refer to as the reducibility judgment. And this is a key portion of our logical relation. So how this works is that we capture the properties of our system by the types. So these are defined by type, basically, and we can then extract properties for them. So we can both extract global properties like normalization, but we can also extract properties that are more local to the specific type, like pi activity. And these judgments also allow us to produce additional properties like consistency. These judgments doesn't handle substitutions, so we therefore have to introduce another set of judgments, which we refer to as validity judgments. And these are basically a set of judgments that basically corresponds to the closure of reducibility under all substitutions. Okay, so now we have introduced a lot of judgments to our system. So now we want to accomplish our proof by doing it in two stages. So we'll do a first stage where we want to prove equivalence between the well-formed judgments and the reducibility judgments. And by doing this, we will be able to extract the properties of normalization and pi activity and have them in the well-formedness setting. In second step, we will generalize the logical relation a bit so that we can accommodate algorithmic equality for it. And this will allow us to prove that that conversion is equivalent to algorithmic equality. Okay, so let's first go into the first stage. This is done by logical relation by proving a fundamental theorem for the well-formedness judgment such that we achieve validity for it. And from validity, we can easily prove reducibility by just applying the identity substitution. And from reducibility, it's trivial that it's well-formed. So these three proofs will give us that they are indeed equivalent, and we'll be able to get the proofs from reducibility. So we will look a bit closer at the reducibility judgment and how they are defined. So the reducibility judgments are defined by induction-recursion, such that the types for these judgments are an inductive part that is mutually defined with a recursive part that is the other judgment. So as we can see here, we define the types inductively and have inductive cases for them. And for the recursive part, we have it so that the dependent type. And we can then do a pattern matching on the types and can then decide what properties these judgments to hold for that certain type. So to more clearly illustrate this, I will go into an example, which is the pi types. So for A to be a reducible type as a pi type, it first has to reduce to a pi type. Secondly, we also need that the components of the pi type is well formed. And we also require that f of this pi type is a reducible type. And we here ignore the Kripke the aspect of here to make this presentation simpler. But we here use a Kripke aspect here. Next, we require that for all A's of type F in the reducible relation, it holds that if we apply A to G, G is a reducible type. And we also require that if A and B are equivalent reducibly of type F, then if we apply A to G and B to G, those are reducible equivalents. And these basically captures the properties we need to represent the pi types. And we will also use these properties for the next part of the judgment, which is the type equality or type equivalence. So for A and B to be equivalent as pi types, we require also that B reduces to a pi type. And these pi types then have to be equivalent by conversion. And again, with the reducible part, we also have that F and F prime has to be reducibly equivalent. And for any A of F, if we apply A to both G and G prime, those have to be reducibly equivalent. And as we can See, by the equivalence relation, which I showed you previously, you can very easily get pi-injectivity from these properties. So we can get from our two last points, we can get these in the well-formalized judgment. And this basically is basically the pi-injectivity. Okay. So we now go to the second stage of our proof. And this will be to generalize the algorithmic equality. So we do this by introducing something we call generic equality. This is another equivalence relation, and it works as a kind of an interface for both algorithmic equality and conversion, such that it is a subrelation of conversion, but it is still weak enough so that we can still accommodate algorithmic equality. As for instance, algorithmic equality doesn't have any reflexivity property that is directly provable. So we will then inject this generic equality in between the reducibility judgment and the well-formulated judgments. And we have an instance for the well-formulated judgment for the generic equality, and we also introduce an instance for the algorithmic equality. And this lets us prove that by also the soundness proof that the algorithmic equality indeed is equivalent with conversion. So now go through some of the formalization statistics. So our formalization, which we have done in Agda, roughly consists of 10,000 lines of code. And 50 of these is used to formalize the logical relation. And if we haven't generalized the logical relation with the generic equality, we would have needed to double this the amount of lines. So by generalizing it, we kind of save some work and some lines of code. And we also have this formalization available on GitHub on this link. So in conclusion, what we have basically accomplished with this proof is that we have formalized a substantial part of the meta theory that we have been working with. However, we still have a large gap between the object theory and the meta theory, which we would like to minimize. And we also accomplished with the inductive-recursion that we've been able to disprove that. And we have showed that it's a very strong property. For instance, with the induction-recursion, you can effectively represent an infinite hierarchy in a single Agda universe. And we also accomplished our proof with a single fundamental proof with 2 instantiations, and this have allowed us to effectively reuse our code. So some of the future work we would like to accomplish with this formalization is that we'd like to extend it to type checking as well. And we would also like to strengthen our object theory and or weaken our meta theory. We would either like to introduce induction recursion to our object theory or remove it from our meta theory or meta theory proof. And some other extent we could do to strengthen our object theories by introducing inductive families and identity types. Okay, so thank you.
We have some time for questions. Yeah. All right. right. So what is the overall plan for? Can we call this the self-verification of Agda, keeping in mind the Gödel restrictions and so on? What would be the overall plan? For instance, if I would like to see verified the version of Agda in current use, let's say, is there a canonical extension to a stronger system that would prove the desired properties of the current version of Agda?
The current version of Agda would be quite tricky to include all its functions because it's quite a large language, and as you could have seen from a previous presentation, we have co-induction there as well, so there's a lot of properties. Would be certainly tricky to bootstrap the entire type theory of Agda, but would be really nice to accomplish that.
Because you had that picture with the object logic and the meta logic moving towards each other, but another option would be the object logic moving at full speed, so to speak, growing up as fast as possible, and then the meta logic moving in the same direction to accommodate the object logic.
Yeah, right now we haven't been able to kind of sync them up first, but it would be nice to be able to show that. That would kind of disprove Gödel's incompleteness theorem as well, in a sense.
Yeah, I mean, this can be disproved on a practical basis, so to speak, by keeping enlarging the meta logic.
Yeah.
Yeah. Okay. Thanks.
Go ahead.
So can you? So I thought that induction recursion in Agda was sort of experimental. So do you know if the sort of the subset of Agda that you use, is that like something that's known to be sound, or what's the?
I'm not too sure how the status of induction recursion Agda is entirely. I mean, I think there is some works that use induction recursion still, but I haven't seen any concrete proof to prove it that it's some. But at the same time, I'm from the perspective that I kind of need to prove it before I see it's completely sound, but as it is now, there's no real proof that it's sound. But again, there is no counter proof as well, so no counter itself.
Well, I have a question. So this work has a lot in common with a little older paper by Harper and Fenning on comparing for equivalence types and terms in the logical framework. Can you compare what you've done to here? You have a lot more machinery, or at least some more machinery than they use there. So can you compare how that's necessary?
Sorry, I haven't really looked too much into that paper, so I can't compare.
All right, well, let's thank our speaker then.